So I think given that we're in the afternoon, let's forego the introductions and just sort of jump into the topic.
Sure,
How does that sound?
Yeah, sounds good.
And maybe I'll start with you, Hiroaki.
Right.
So you have worked both in industry as an executive at Sony and as an academic, as a professor at OIST and elsewhere. What did you learn on the industry side of things about innovation, and what could you do there that you could not do as an academic?
Yeah, I think I have gone through like numbers of academic institutions. I've been at Carnegie Mellon and Caltech with Stephan, and then also spent a lot of time in OIST. OIST actually is not just being the faculty, but actually involved in the creating OIST. And on the other side, I actually was the CTO for Sony Group Corporation, overseeing the quite large number of engineers and researchers, like 3,000 people reporting to me, and then I have to oversee like 100,000 engineers group-wide. So the difference is quite dramatic. I think like a common theme is to create new things, like all the either the new science or new technology. We actually passionate about like creating something new, and that help people or like contribute to the people. But at the same time, like the corporate environment is more on the value driven, the value to actually make things better in the market. So it's more on the focused. And then, although like a corporate has like a much broader range of scope than the product itself, at the end of the day, you have to come up with the products and services. That's the final goal of the enterprise. So for the Sony, we have like the research groups or like engineering team, which actually gear toward a specific series of specific products and services, either short term or longer term. This is aligned with the corporate strategy. And we have like a Blue Sky lab, which I still manage, like Sony Computer Science Lab, which is not really involved in the Sony's like a direct business, but we have a freedom to whatever we want. We have like AI, we have agriculture, we have like a music guys, and then we have all kinds of things. So this is very fortunate to be able to have this Blue Sky. So this part is more or less similar to the academic environment. But this is rather exceptions. And then also I created, last 5 years, we created the Sony AI, which is a top-notch AI research group, which publishes Nature's, and then the one just accepted, things like that. But this one is strategic position to have a long-term implication to Sony's business. So it's not completely blue sky. We have like a basic research, but geared toward this, impact in the 5-10 years term. Mm-hmm. So that's like, I think like, companies more like, focused, and then although company may have a much broader scope, that's have somewhat linked, short-term or long-term linked to the corporate goal. Mm-hmm. So that's a difference. Whether in academia is pretty much like an individual curiosity-driven, and then you take it from there. Right? So that's like a big difference. I think.
Mm-hmm. Got it. And you now have many contributions, and you have the benefit of time from some of the earliest ones. And so let's go back to the RoboCup.
Oh, yeah, sure.
Okay.
Yeah.
And you started that quite some time ago.
Yeah.
Maybe you could speak a little bit about that and tell us what the ultimate impact has been, and the innovations that have resulted from that.
Right. Those who may not know, RoboCup is a global AI robotics initiative. It's a grand challenge to build like a fully autonomous humanoid robot to win the World Cup champion in soccer by 2050. So we started this like early 90s, and the very first competition started in 1997. And this is supposed to be fully autonomous humanoid robot. And then, because of a soccer game, like, people get excited about this, and thousands of researchers from over 35 countries get together. So this is really the competition-driven, exploratory research project. And what is interesting here is like a passion drive things, actually. So because of the football or soccer, like, everyone is passionate. People, like, if you got the final game between the robotics team, between Germany and Italy, okay, things are gonna be crazy. It's not robot, it's a soccer, okay? So in the soccer, they have to win, okay? So that's interesting and passion drive. And the other thing is like openness of the collaboration, because it's became like a big community. And then a lot of interesting research and award-winning research came out, and also a lot of spin-out. So one of the things we found out like interesting is like first 5 years, we have like quite a number of spin-outs, and one most successful one is the Kiba system. So they took like a robot, autonomous robot technology built in RoboCup to the warehouse management and do the autonomous warehouse management system. And later, this company acquired by Amazon and turned into the Amazon Robotics, and now sweeping change of the warehouse, management industry. So, and then more, companies coming in. Right now, like a big humanoid company called the Busa Robotics in China, they have been building robots for the RoboCup, and then now they decide to go for the, humanoid. And the RoboCup is now really focused on the humanoid, so it's going to be really the big booster. So what I learned from RoboCup is like you have to have a big vision, and you have like a systematic organization construction to be able to self-sustainable. And then also like, vision need to be kind of linked to something very practical, right? So like why we pick a soccer game is like in a soccer, we have every element we need in the robotics and AI in the real world, today. So like we envisioned this in the early 90s, like we envisioned like 30 to 40 years from that time, right? So this is the, now it's the time. What is the most important thing in robotics and AI, like autonomous driving, like warehouse management, disaster rescue, and home care, and what is all the technical elements which will be important, and then we actually redefine, reassemble it into the single task, which everyone can get excited about this, and then we come up with the soccer game. So that I think that is really important for this kind of research is the visions and then the rationale behind the visions and how you actually can impact that vision to the real industry and the society. And if you actually need to, if you can combine it together, I think like it'll be good. And then one more thing is like, this will be done by the people. So like organization and self-sustainable structure need to be embedded. And that is a part I spend a lot of time actually.
Mm-hmm. Amazing, thank you. So, Jacob, you were recognized this year with the Nakasone Prize for your work on synthetic embryo models. Congratulations. Maybe you could tell us, and very amazing research. Maybe you could tell us a bit about how you got to that and what drove you to do that, and then what you think the first sort of real applications to human health will be of that work.
Yes. So, I mean, we got to that a little bit kind of by different directions. One thing we're very much interested in is, so we work on stem cells and how they differentiate. And us and others in the field were trying to make what's called interspecies chimera, meaning you can take, for example, human cells and try to inject them into a very early mouse embryo at very early stages and try to learn how the cells migrate. And then usually you put them inside the mouse uterus, and it would work inefficiently, of course. But then we will realize that really the uterus is a black box. So you don't know what's happening, and we go on a snapshot. And we really wanted to get into being able to see what happens inside the mouse uterus. That was one aspect. And then a second aspect that we were studying is really how we work on stem cells, and stem cells come in different flavors, and there are cells we've worked on which is called naive stem cells, meaning that very, very primitive. We say even they're almost similar to yeast. They can live as haploids, actually. They don't need a lot of fancy mechanisms. But then also they turn out to be very good as a starting material for differentiation, but we wanted to understand really how does differentiation work. And when you talk about, if you want to take stem cells and want to drive them to become like organs, you want to imitate what happens inside the embryo. But actually, in the case, of course, in humans, we don't have access for justified ethical reasons to see embryogenesis happening. So we don't know actually what to imitate. Therefore, there was this need to both think about how to mimic embryogenesis, even if it's not identical outside the uterus, and also just like actually when you want to understand a car, you take it apart and you build it. So also take these stem cells and not only derive them from embryos, but then actually try to build something similar to an embryo outside the uterus. And so that's kind of the goal. So of course, very curiosity, perhaps not directed. But then quickly, of course, there are, I think, obvious potential applications, which were not there yet. But just to give you an example, for example, if you think about drug testing today, there are a lot of drugs that actually, today basically you cannot, if you have a good drug, you cannot just test it on pregnant women, even if there is no evidence that it's actually teratogenic, just because the FDA doesn't want to take a risk. And you can envision, and we showed that with mice, that actually now you can take this drug and put it on an embryo model outside the uterus, and we can really recapitulate teratogenic known effects on these models. So you could think maybe a dream that we can really use this as a platform. Perhaps there's now a way in between. Maybe if we can show that a drug that is actually safe in that test, and maybe then you can able to test it on some clinical applications. This is important because there are companies like Novo Nordisk and others that advanced with drugs and invested billions, and then everything collapsed because it turns out to be actually damaged. So there's that aspect of things. And then, of course, in case of modeling embryogenesis, and then we talk about human development, really in the first 4 weeks of development, which I call it like the drama, basically most pregnancy failures happen then, most developmental defects happen then. That's why, for pregnant women, they say, particularly don't drink alcohol early on, or why CMV infection is really bad early on. So this is a sensitive area. And then you could think that if you are able to maybe have a system that recapitulates some of these aspects, you can perhaps again study whether it's a CMV pathogenesis, whether it's about the effects of these drugs from that aspect. And of course, the third aspect, perhaps you could look at it as a differentiation assay, because what we do is basically, what we are showing is that these naive stem cells are perhaps in a way our kind of single cell ancestor, and what we're doing is we're unleashing their ability to, I call it like embryogenesis nucleation, to start and self-organize, I don't like that word actually, but really create different tissues. So this is actually your kind of different self-driven differentiation, and we can see really the quality of cells is much, much higher than actually what you typically get from what's called directed differentiation. So that's one other aspect. Can this be a kind of a differentiation assay as a starting material for cells? And that's another, I think, aspect that needs to be explored.
Amazing. So maybe another question for Hiroaki here. A few years ago, you wrote a paper in which you issued a Nobel Turing Challenge to the community.
Yes.
And maybe you could reflect on that a little bit, a couple years down the road.
Sure.
And is that the secret sauce that's going into your startup company?
I think this is probably a very appropriate place to discuss about this. Like this Nobel Turing Challenge is this AI and robotics grand challenge, not like a notebook, a very different one. Started like a few years back. Is like can we actually build AI machine, AI system to be able to continuously make major discoveries, some of them worth Nobel Prize or probably beyond. And then, this is a challenge and the question. Challenge is, can you build that? Okay, the question is, if you manage to build it, does the machine behave like a best human scientist? So potentially it can pass a Turing test. Does machine exhibit very different kind of intelligence? So obviously different, emerging different pattern intelligence. So this is really getting into like a science of the science. And a lot of people got interested. A lot of people working on the AI for science as AI for tools for the scientists. But at the same time, many researchers getting interested in can we actually build autonomy on the autonomous AI scientists to be able to run the experiments, come up with the hypothesis, do the experiments fully autonomously or highly autonomously. So I think we see a lot of implication on this. Because for example, in a human genome, we have 40,000 genes, but almost half of them have no paper. People want to bet on the gene that seems to be important. So but this long tail part is not investigated. But many genes out from that turn into very important specific disease. But if AI and robotics can be used, we can actually do a broader scope, brute force exploration, the entire search space. And that's human tend not to do that because we want to be successful, we want to be contribute, and we want to bet on this. So what we can do with this as a new modality of science is massive knowledge extraction and consolidations, massive hypothesis generation. When we do the research, we come with the 1 or 2 hypotheses, expecting this is going to be the great one. But instead of that, can we actually populate the entire hypothesis space, which generates logically consistent, and then rank that with the possible likelihood they're going to be successful, design experiments, massive experiments. We need robotics to do that. We actually, in Okinawa, we're building that kind of robotics right now. Some of them is also operational. And then verify that, do in cycle. I think this is going to be the warp drive for the science. Not every science, but a significant part of science, because we're going to have a lot of hypotheses, a lot of experiments, many of them all together. And I think this can be accelerated. But at the same time, like, can we actually, AI can have like some new conceptualization, not just a discovery of the specific thing at large scale. Like, can we AI come up with a concept like a checkpoint, for example, or cell cycle, you know? That's another challenge, right? So like a discovery associated with the concept formations, that's harder part. Or like, can we actually come up with like a two dot that's far apart to be connected? For example, like, can we replicate or do something like a CRISPR-Cas9 discovery? It's really connecting, you know, two dots far apart, and can AI to be able to do that, or can we do it better? I think it's a long, you know, long and winding road away, but I think this is one of the most interesting projects we can have.
Terrific. All right. Well, Hiroaki, Jacob, thank you so much for a scintillating conversation. I'd like to